All right, here we have some practice problems. So we've already seen that in terms of positive definite functions, we can have locally positive definite functions. Here we've gone through and shown using partition matrices, we can take our matrix, we can partition it, and we can go through and establish that it is positive definite. So in this case, I have these four matrices. Notice that this matrix has its transpose here. This matrix is symmetric. This matrix is symmetric. I look at this matrix, I call it Q, and I can see it's positive definite. I have its eigenvalues along the diagonal. It's a symmetric matrix with positive eigenvalues. Therefore, it is positive definite. I have this matrix, which I can actually go through and show is I have positive elements along the diagonal, and its determinant is 49 minus 4, which is positive. And so it is a positive definite matrix too. Now, I can go through and form the Schur complement. So R S transpose Q inverse S, multiply it all out, and I get this expression. This has positive elements along the diagonal, and its determinant is this quantity, which is strictly positive definite. Strictly positive. Therefore, this quantity is positive as a positive definite matrix. The Schur complement is a positive definite matrix. So since Q and its Schur complement are positive definite, that means P was positive definite. So this is one way of checking the definiteness of a matrix where we can partition it. All right, let's look at derivative along a system trajectory. So here, x1 dot, x2 dot is given by this expression. These are functions of x1 and x2. Okay, and I'm going to choose this as my Lyapunov function. So this is my P. Okay, the derivative along the trajectory of the system S, so the gradient of this with respect to S is actually 2 times x transpose times this matrix. So 2 times x transpose is x1 and x2 times this gives this. So 2 times x transpose times P is this, and then times F. And we multiply these two vectors together, we get a scalar quantity in x. Scalar function of x. So this is the derivative of a function along the system trajectory. This is an example of that. Now, in order, again, to be a Lyapunov function, we need v to be a positive definite function and its derivative with respect to time to be a negative definite function. Let's look at this example. X dot is equal to minus 2x cubed, and we consider this candidate Lyapunov function. Again, this is a positive definite function because when x is positive, this quantity is greater than 1. When x is non-zero, this quantity is greater than 1. When x is equal to 0, this is equal to 1, and so we get 0. So this is the positive definite function. We take the derivative along the system trajectory. So the gradient of this with respect to x is this quantity. In this case, it's a scalar quantity of a scalar, so that makes it simple. So this derivative, the derivative of this with respect to x is 2x e to the x squared. Okay? And then times this, multiplying this out, we get this expression, which is a positive definite function. Negative definite. This quantity here is positive for all x, and it's only 0 when x is equal to 0. So here we have, this is a negative definite function. So it's negative of a positive definite. So the derivative along the system trajectory is a negative definite function. Thus, v is a Lyapunov function, proving the system is stable. Okay, so this is actually asymptotically stable. So let's look at a linear example. X dot is equal to ax, a scalar linear version. That doesn't get any simpler than that. And our quadratic, we have our quadratic Lyapunov function, which is, again, as simple as possible. So PDF, positive definite function. So the derivative along the system trajectory, so derivative of this is 2x. System trajectory is x dot. And so x dot is equal to ax. And so we get this expression. This will be negative definite if and only if a is negative. If a is strictly negative, we will have this. But if you look at our original system, x dot is equal to ax, we know that this system is stable only if the eigenvalue is negative, right? Has a negative real part. That means a must be negative, so we actually get the same result. All right. So here's a nonlinear system. X dot is equal to minus sine of x. I'm going to consider this candidate Lyapunov function. We can actually go through and show that this function, as weird as it looks, is actually a positive definite function. If x is 0, I'm taking the integral from 0 to 0, which is 0. When x is positive, the integral of sine of y from 0 to something positive, the sine, that's going to give me the cosine, right? And so the cosine is going to be positive, but it's local, right? It's only up to a certain point. So sine, the sine function is positive only up to pi. So 0 up to pi is this positive. All right, so we have that. That's why it's local. Derivative along the system trajectory, v dot. So derivative of this with respect to x is sine of x times this, which gives minus sine squared. So it's like, now why would you choose? Well, the reason we choose this function is because the derivative of this with respect to x is that. Okay, and so we get minus that squared, which we can show is locally negative definite. This quantity is locally, so when x is 0, this is 0. When x is non-zero near the origin, this is negative. So v then is a Lyapunov function, and the system S is locally asymptotically stable. All right, how about this nonlinear function? X dot is equal to minus c of x, where c is just some function of x that satisfies this property. X adjoint, x transpose, times c is positive for all x non-zero. Okay, so that's what this is saying. And we're going to choose as our candidate Lyapunov function just the 2 norm squared. Do you take the derivative along the system trajectory? So the derivative of this with respect to x is 2x adjoint, and times the derivative, and so we get the derivative is just this quantity minus c of x, but x adjoint c of x we know must be positive, so this is locally negative definite. Okay, so we have a positive definite Lyapunov function, locally negative definite derivative, and so since this is true for all x, then it is globally asymptotically stable. So what kind of a C function does this? Well, in the scalar case, we would actually have a function that looks like this. So this is x, this axis is x, this axis is c of x, and it's a function that has its values only in these 2 quadrants. Okay? So if x is in this quadrant and c of x is in this quadrant, then when you multiply the 2 together, you get something positive. So that's basically what this is saying. I'm getting functions that are like in these quadrants. That's what that's saying. So, but notice this c of x can be any function. So this actually considers a wide class, a whole class of systems we have just shown to be stable. Okay, any system that is of this form we have shown to be stable. All right, what about this system? This is a nonlinear system because this is cubed, right? And so this is f of x. We're going to choose this candidate Lyapunov function, x transpose px, where p is this matrix, and a is going to be a positive quantity. We don't know what a is yet. Okay? And so I have the system. I want to prove that it's stable, but I'm not sure exactly what Lyapunov function to choose. So it turns out you can choose a Lyapunov function, but that Lyapunov function might not have a negative definite derivative. Okay? Because again, it's not just about the function, it's also about the system trajectory. And so the two kind of go together. And so just because you have a positive definite Lyapunov candidate, that doesn't guarantee anything about the derivative. So what I've shown you to this point are examples, but there are plenty of other examples that show where it doesn't work. Okay, so radially unbounded. All right, so this is a positive definite matrix and radially unbounded function. Okay, so I just need to find out what A is. So I'm leaving it as a variable for now, and I want to come back later and find out what A must be in order for the system to be shown to be stable by proof of a Lyapunov theory, the Lyapunov function. Okay, so how do we pick A? That's the question. All right, so we go through and compute the derivative along the system trajectory. So this is what we get. We multiply this out, we get this scalar quantity, and now I have these three things. Now notice that what happens when I get these, well, I get these three terms. This thing is strictly negative. This thing is strictly negative. And that actually should say x2 to the fourth. And then I have this other thing here in the middle. This other thing. I can go through and show that if A is equal to 4, this thing in the middle goes away and we're left with this expression, which is globally negative definite. And so this proves that our system is globally asymptotically stable if we choose A equals 4. Now, A equals 4 just kind of popped out here because that actually made these cross terms 0. It turns out you can actually have other values, and you can actually go through and show that there are other values of A that will make this work. But here is A value. We don't need infinite number of values. We just need A value, and this certainly does work. All right, well, let's look at a real system instead of just the math. So in this case, we're going to look at the system of a pendulum. So the pendulum has two states, the angle of the pendulum and the velocity. Okay, so position and velocity, in this case angular position, angular velocity, are common state variables for mechanical systems. So x1 dot, x2 dot, this is what I get for x1 dot, x2 dot for this pendulum. So it's a nonlinear function and depends upon both x1 and x2. In the system, there's B, which stands for the viscous friction. So there's friction in the pivot. Okay. So we can look at energy here in terms of its, this is its kinetic energy, right? 1/2 mv squared, or in this case, J theta dot squared. Okay, this is the kinetic energy. This expression is the expression for the potential energy. So the potential energy is the energy associated with lifting it up according to gravity. So gravity is acting on this thing. So this is the kinetic energy, and this is the potential energy. And so T, we're going to call as the energy, is the potential energy, kinetic energy, and the potential energy. V is this energy plus these two friction terms. I'm going to add these friction terms onto V. Okay, so notice that these two terms do not include friction. So if we go through and compute, so incidentally, both of these functions are locally positive definite functions. Okay, this is positive definite, and actually the reason we have this term here is actually to make things positive definite. So anyway, this is positive with respect to x2. This is positive, locally positive with respect to x1, and so this is locally positive definite. This is also locally positive definite. So we have local positive definite for both of these functions. When we take the derivative along the system trajectory of t, we get this quantity, which is locally negative semi-definite. It's not negative definite because of the fact that this function can be 0 when x1 is, when x2 is 0, this function will be 0 even if x1 is not 0. Okay, so we have that. V dot, on the other hand, which is the derivative along the system trajectory for V, is given by this expression, which we can actually go through and show is locally negative definite. Okay, not just negative semi-definite, because notice this actually includes the same term here in x2, but it also includes this term that includes x1. And this is actually one of those things that has its thing in sector A and sector 1 and sector 3, quadrant A, quadrant 3. This function here. And so this is locally negative definite. It's the same system. But this t didn't actually give us positive definite, negative definite. It gave us positive definite, negative semi-definite. Okay? So, but the same system, I can define a v, which is different, which is positive definite, negative definite. So we have that. So if I were to actually start with some initial condition on this pendulum, and I were to plot t and v as functions of time. Here's my plot. Okay, so these are actually plotted. Notice they're very similar to one another. They're very similar to one another. They're actually lying right on top of each other. They're not identical. So I'm going to zoom into some portion here. Boom. And I can see the energy, t, is this function. Whereas v, which is the other thing that included the friction, is this function. So notice that this function has a strictly decreasing derivative. The derivative is constantly negative. It's smoothly negative. Whereas this function here, notice that it goes through a zero derivative at some points. That is, it's locally negative semi-definite. Okay, so the derivative here is always negative, strictly negative, but for this guy, it actually goes through zero at some point. Okay, has zero slope at this point. Zero slope at this point. And so that's why the function t, which was actual energy, the function t wasn't a sufficient Lyapunov theory. So it's not exactly energy, it's energy plus something. In this case, it's not only the energy like kinetic and potential energy in the system, it also is the dissipated energy in the system. So by adding the dissipated energy in the system, we got a true Lyapunov function. Okay. So the energy in the function does not take into account the dissipation. So basically, when we looked at our system, this is the energy in the system. This is our kinetic and our potential energy. These two terms basically describe the energy that's leaving the system. All right, so let's take a look at this as we vary our friction, our B. Okay, so here are two responses, two views when we have B equal 0.5. So I've started off at at this initial condition in both cases. So I'm basically just looking at the plot from two different perspectives. Okay, actually there are two different functions here. So one is taking longer to settle than the other. Here's another case. So I'm using, again, a comet plot in 3D. And so this is what we're getting. So this parabola is actually our Lyapunov function. Okay, here is a quadratic stability example. So I have this, again, nonlinear system. So nonlinear systems are actually fun to work with in these cases because of the fact that we know for a linear system, you check the eigenvalues, boom, you're done. Okay, so that's a simple way of doing it. The reason we're actually looking at Lyapunov is two reasons. One, that gives us a slight handle on being able to do nonlinear systems. The second reason is because it turns out that the Lyapunov function for linear systems can actually be used not just for what can be used for more than just stability testing. And we'll come back in later and see what that is. All right, so I'm given this system, and I'm assuming local stability. That is, x1 is between -50 and 50. So we have this system, and we're looking at it locally. So local in terms of x1, not necessarily in terms of x2. Here is my quadratic Lyapunov function. I have a p that I'm a positive definite matrix. I go through and compute the derivative along the system trajectory. So when I multiply this out, I get this expression. I can factor this expression this way. Okay, so it's like, now how did he know to do that, right? How did I know? So the fact is, I have x1s, x2s. I have cross products between the two, and so I am looking for something of this form. Okay, and so I start with a q, and I don't know what q is, but I know what x1, I know what x should look like, right? And so I start with q11, q12. This is also q12 since it's symmetric, and then q13. So I have three unknowns. I multiply it out, and I want it to be equal to this, and that's how I solve for. That's actually how I solve for q. So it looks mysterious here. It's actually not that mysterious. So I've got a function now, and I have written it in this form. Now we need to check what's going on with q. So for quadratic stability, we need to have this inequality satisfied. Q minus alpha I must be strictly greater than 0, greater than or equal to 0. So q of x minus alpha I is this expression. So remember, a 2 by 2 matrix is positive definite if the diagonal elements are positive and if the determinant is positive. So clearly this needs to be greater than 0. Or another way of looking at it is a quantity and its an element along the diagonal and its Schur complement must both be positive. So this quantity is greater than or equal. We need that. And then we need the Schur complement. The Schur complement says this. Okay, so this minus this quantity squared divided by that. And so I need these two conditions to be satisfied in order for this inequality to be satisfied. Now remember, x1 is actually local. That is, it's between -50 and 50. And so I can try the different values and show that alpha between 0 and this quantity, okay, that quantity coming from here, for alpha in this region, we will have q, so the alpha in that region will satisfy both of these inequalities. Okay, notice that this is less than 4, so that means 4 minus that is going to be positive. Okay, and so, but overall we have this matrix inequality. So in this case, the system will be quadratically stable, and we actually know, and so we've proven that it's not only stable, it's quadratically stable. It's not asymptotically stable, it's quadratically stable. So we've proven that. Now we've actually shown or stated or kind of talked about the fact that if a system is quadratically stable, it's automatically exponentially stable. But let's go and look at the exponential stability anyway. So exponential stability means we need to check this kind of inequality. Okay, so instead of having I here, I have P. So Q minus alpha P is this expression. So notice it's very similar to what we had before, but not quite. Notice here I have a 4 alpha. Okay, and then its Schur complement is this. Both of these need to be non-negative. Actually, they need to be strictly positive. Again, for alpha, for x1 restricted between -50 and 50, I get this expression. And so notice that here I have a number, and so alpha between 0 and this number guarantees my system will be exponentially stable. Notice that this number is smaller than the number we got for the quadratic stability. So anyway, we have that condition. So we've shown quadratic stability and exponential stability for the same system. All right, for time-varying systems, we had the issue of decrescency. And so we have this condition, and we actually went through and showed that this system is not this v is not decrescent. So decrescent depends not only upon the function itself in terms of x, but how the function responds with respect to t. And in this case, it blows up with respect to t, and so it's not decrescent. So we can't have it blowing up with respect to t. It actually, the function needs to be bounded with respect to t. So what about this function? Well, we can see it's positive definite. The function is radially unbounded in x, but it's not decrescent. We've seen that. What about this function? This function is positive definite in x. It's not time dependent. Therefore, it is decrescent. Okay? So anytime you have a function that's not time dependent, then it is decrescent. What about radially unbounded? This function is not radially unbounded in the x1 direction. It is radially unbounded in the x2 direction, but you actually need it radially unbounded in all directions. So we have this function. It is decrescent. What about this function? So in this case, we can find a constant value k1 such that v1 is greater than or equal to k1 times x transpose x. So this implies that v is positive definite for all time. We can also find a constant x2 so that the absolute value of v of x of t is less than or equal to the norm for all time. And because it's bounded now by a norm, a constant times the norm, it is decrescent. This function also is radially unbounded in x. So this function is decrescent in time. So it's not impossible to find decrescent functions, but to find a decrescent function that makes your system have negative semi-definite or negative definite can be a challenge. So one of the challenges of working with Lyapunov functions is that you have to find a Lyapunov function. A quadratic function is a good place to start, but a quadratic function is not guaranteed to work for you. And so you need to find a function that actually works. So what the Lyapunov theory tells us is it tells us when our system is stable. It doesn't tell us specifically about the instability of our system. So we'll come back and look at that as well. So these are the practice problems. We have this example problem, discrete time system. x1 depends upon x2. x2 depends upon both x1 and x2 in a nonlinear way. If I look at this function, I notice that the denominator is the same in both terms. And so as a vector, x of t plus 1 is equal to 1 over this quantity times the vector x2 and x1. Our candidate Lyapunov function is just the norm squared, which is positive definite and radially unbounded. Okay, so taking the difference along the system trajectory, delta v of x of t is equal to v of f of x of t minus v of x of t. So this is just the norm. So x transpose x. So this is f transpose f. Okay, and so this is what f transpose f looks like. If I multiply this out, this row times this column is actually equal to v of x of t. That's just the norm of x of t. So it's just written in opposite order, and then divided by this quantity. So I can, out of all of this, I can factor out v of x of t, and I get this. If I look at this quantity here, this denominator is greater than or equal to 1 for all x. So that means this is less than or equal to 1 for all x. And so all of this is strictly non-negative, non-positive for all x. But when x2 is 0, this will be 0. So this function is globally negative semi-definite. It's not negative definite. And as a result, we only get stable in the sense of Lyapunov out of all of this. Let's look at the same system, except instead of just having 1 here, I have a 2. So that makes this smaller, which is actually works to the advantage. It considers the same Lyapunov function as before. And so when I take f transpose x, notice that I have this 4 here. And again, this times this gives v of x. I can factor out v of x, and I get this expression. Okay, so now I look at this quantity. This quantity is less than or equal to 1/4 for all x. So 1/4 minus 1, this quantity is going to be negative for all x. And so this function is globally negative definite. And since it is globally negative definite, and since v was radially unbounded, then the system is globally asymptotically stable. So we have that.